Imagine building a 33.9-kilometer wall across the open sea, not across a river, not along a coastline, but directly through the tidal waters of South Korea's Yellow Sea. Twice every day, tides rise and fall by roughly 6 meters. Currents can become powerful enough to move massive rocks across the seabed. And underneath it all is not solid rock, but layers of soft, unstable tidal mud. Yet South Korea built the wall anyway. The project took 19 years, transformed hundreds of square kilometers of coastal water into reclaimed land, and became one of the most ambitious coastal engineering projects ever attempted. This is the story of the Saemangeum seawall, how engineers fought the tides, closed enormous gaps in the sea, and created new land where ocean water had existed for thousands of years. The story begins in 1991, when South Korea officially began the Saemangeum reclamation project along the country's southwest coast. The plan was enormous: construct a continuous seawall stretching 33.9 kilometers between Gunsan and the Byeonsan Peninsula, closing off the mouths of the Saemangeum and Dongjin rivers, and enclosing approximately 401 square kilometers of tidal waters and mudflats. The ultimate goal was not simply to build a wall. Behind it, South Korea planned to create new land for agriculture, industry, infrastructure, and eventually a major new urban development. The scale was extraordinary. The enclosed area was roughly 2/3 the size of Seoul, creating an enormous new territory from what had previously been sea and tidal flats. But before the first major section could rise above the water, engineers had to solve the most basic problem. What do you build on when the ground itself behaves like liquid? The southwest coast of Korea contains vast tidal flats made from sediment carried down by rivers over thousands of years. At low tide, enormous areas of gray mud are exposed. At high tide, they disappear beneath meters of seawater. This sediment is saturated, soft, and unstable. Put hundreds of thousands of tons on top of it too quickly, and the foundation can settle unevenly or shift. So engineers had to prepare the seabed before constructing the seawall. Massive dredging equipment was brought offshore, including cutter suction dredgers capable of removing enormous quantities of sediment. Their rotating cutter heads broke apart the soft material, while pumps moved the resulting slurry through pipelines. In some areas, engineers had to excavate through many meters of unstable sediment before reaching stronger layers capable of supporting the structure. And there was another problem. The tide never stopped. A trench that looked clean at low tide could quickly fill with sediment when the water returned. Barges carrying thousands of tons of rock had only brief windows to move into position, unload, and escape before powerful currents returned. One timing mistake could turn a routine operation into a disaster, so every movement had to be carefully coordinated with the tides. Once the foundation was ready, construction of the seawall could begin. This was not a vertical concrete barrier, but a massive earth and rock embankment built across the sea. Its average height is around 36 meters, with some sections reaching 54 meters from the seabed to the top. Most of it remains underwater. At its widest, the base stretches hundreds of meters across, creating what is essentially an artificial mountain beneath the Yellow Sea. Millions of tons of sand and fill were placed in controlled layers and compacted to strengthen the structure. Geotextile systems helped contain the material during construction. The outer face was then protected with layers of rock, forming a sloped armor designed to absorb wave energy rather than allowing waves to strike a solid vertical wall. But the hardest part was still ahead: closing the remaining gaps. As the openings became smaller, the same enormous volume of tidal water was forced through narrower channels, dramatically increasing the current. Loose rocks could simply be swept away. Engineers responded by gradually raising the seabed itself. Rock and rock-filled structures were placed into the openings to create underwater sills. One key tool was the gabion, a strong wire container packed with rocks. Unlike loose stones, gabions stayed together under powerful currents, settling and locking against each other. The northern gap was finally closed in June 2003, but that success created a new danger. With fewer openings remaining, the tidal forces on the final gaps became even stronger. The most difficult closure operation was still to come. On April 21, 2006, engineers faced the final and most dangerous stage of the Saemangeum seawall: closing the two remaining gaps. Both had to be closed together. If one closed first, the enormous volume of tidal water would be forced through the other, creating currents strong enough to sweep away the construction material. As the tide approached slack water, the current weakened. Then the signal came. Convoys of trucks began dumping rock, while cranes lowered heavy blocks and gabion structures into the gaps. Bulldozers pushed material toward the water as engineers monitored the current and seabed in real time. The sea fought back. Some rocks disappeared instantly, but enough remained for the underwater sills to rise. Then the tide reversed, attacking the new barriers from the opposite direction. The crews repeated the process again and again. Dump, settle, measure, adjust, and dump again. Eventually, the water became shallow enough that the current could no longer move the heavier material. The gaps were closed. For the first time, the Saemangeum estuary was separated from the Yellow Sea by a continuous 33.9-kilometer seawall. But the battle was not over. South Korea's western coast faces powerful storms and typhoons, capable of producing massive waves and storm surges. Engineers reinforced the seawall with layers of interlocking rock to protect the embankment from erosion. Floodgates were also installed to control water levels and manage the flow between the enclosed area and the sea. After 19 years of construction, the seawall officially opened in April 2010. It enclosed approximately 401 square kilometers and became one of the world's longest seawalls. Behind it, the real transformation began. Engineers drained sections of the enclosed area and used sand and dredged material to raise the ground. Former mudflats gradually became land for roads, factories, infrastructure, and future development. But the project came with a major environmental cost. Before the wall, the Saemangeum tidal flats were an important feeding ground for migratory shorebirds along the East Asian-Australasian flyway. When the tidal cycle was disrupted, mudflats dried, marine organisms declined, and birds lost a critical source of food. Local fishing communities also lost access to shellfish, fish, seaweed, and other resources that had supported generations of families. That is what makes Saemangeum so complicated. From an engineering perspective, the seawall is extraordinary. From an environmental perspective, it shows the enormous consequences of transforming an ecosystem on such a massive scale. Today, roads and industrial projects occupy land that was once underwater. Yet the sea remains on the other side of the wall, constantly testing the structure with every tide and storm. The ocean was never defeated, it was only held back. And that may be the most remarkable part of South Korea's giant wall across the sea. It transformed 401 square kilometers of coastline, but it also created a permanent reminder that engineering can reshape nature without ever completely controlling it. If you enjoyed this story, like the video, subscribe, and turn on notifications for more incredible engineering projects from around the world.